Welcome back to our last video on block shear. In this example problem, we're going to take a look at a double channel connection to a splice plate, and we're going to check the block shear capacity of it. So go ahead and orient yourself with the problem. We have the spacing between the bolts. Again, we have double channels on both sides attached to a 1x12 splice plate. All the steel A36 3/4 inch bolts are what we're going to use in standard holes. In this example, I'm only going to check block shear. I'm not going to check yielding and fracture. We checked yielding and fracture two lessons ago in the videos from lesson 17. If you want to head back there, you can take a look. So all I'm going to do is look at the block shear strength. To remind you what the block shear strength is, I have the equation kind of written here. I pasted it from the code. So you see that the nominal strength in block shear is equal to 0.60 F sub U times A and V plus UBS FU A and T, which has to be less than or equal to 0.6 FY AGV plus UBS FU A and T. Phi is going to be 0.75 because, once again, block shear is a rupture limit state, so we use phi equal to 0.75 for design. Just a note, phi PN and phi RN are going to be kind of the same thing. RN is just kind of nomenclature from AISC, in which it's the nominal resistance of each little segment, and then we're going to add up all those segments for a particular piece. In this case, the capacity that we come up with for this strength and shear and the strength and tension will be our block shear capacity. UBS is going to be 1.0 for this because it is a tension member. And again, refreshing our minds, A36 steel has a yield stress of 36 KSI and an ultimate stress of 58 KSI. So let's go ahead and take a look at our first block that we might suspect failure. And so again, I'm going to start by checking the double channel member for failure, and then we'll have to check the splice plate for block shear failure as well. All right, so take a guess at what you think the failure is. Typically, we would start on the outer lines of our connection, and we're going to draw our shear failures. This is where I usually like to start, draw a shear failure, and now I need to connect these two with some sort of tension failure. So the first one I usually check is just straight across. So what happens if this is the block that we consider for failure? All right, so we have two shear surfaces and we have one net tension surface, and that's for each channel section. So we just have to be careful when we do our calculations that we account for both channel sections in the total block shear strength at this connection. All right, so I'm going to do all my calculations for just one of these channels. And let me divide my page up a little bit so you can clearly separate the calculations here from the information above. So I'll start with the net tension area, and the net tension area is going to be just like we calculate the net tension area for fracture. So in fracture, we consider pretty much like the overall width of the block, but then we have to subtract out the bolt holes, or the number of bolt holes that we go through across that width. So in this particular problem, the width is 7.5 inches, but then we have to subtract out the bolt holes. Now, we have the bolt hole at the top of the red line, and we have the bolt hole at the bottom. But along that net tension area, we're only really going through half a bolt on the top and half a bolt on the bottom. So I'll write that in here as half plus a half. So it's going to be one bolt hole that we have to lose because of that net tension area. So think of the net tension area as going from the center line to the center line of the two bolts. Again, like fracture, we have to consider that we can't just use the diameter of the bolt. We have to add 1/8 of an inch for the fact that we're using standard holes, which are 1/16 inch oversized. And then we're going to use a 1/16 inch for potential damage when we make this connection. Lastly, we're going to multiply the area by the thickness. And in this case, we need to multiply by the thickness of the channel because it's the channel web that's going to be block shearing. So the shear surface and the failure surface here is all in the web of the channel. So I've looked up the thickness of the web of the channel to be 0.379 inches. And you can get that from part 1 in your manual. All right, I'll repeat this process for the net shear area. So in total length, the net shear area is 8 inches long. And now I'm going to subtract out 2.5 bolt holes. So if we look at the green surface, it goes through 1, 2.5 bolt holes along one of those lines. So I do 8 inches minus 2.5 times 3/4 plus 1/8 of an inch. And then we multiply that by the thickness of the web. Now I'm going to multiply this by 2 sides because in the block that I've drawn, I have 2 green lines, 2 longitudinal green lines there. So I have the top green line and the bottom green line. So that gives me 2 sides, okay? So that comes out to a total of 4.406 inches squared. Finally, I need to look at the gross shear area along that green line. The gross shear area doesn't have the subtractions for the bolt holes, so we just take the 8 inches times the 0.379 inches for the thickness of the channel web times the 2 sides again, and that'll give us a value of 6.064 inches squared. All right, once we have these values calculated, we're pretty much ready to calculate the block shear strength for the connection. So I'm going to follow the formula there for Rn that's listed. So I'm going to say basically my total load, P sub u, has to be less than phi, which is 0.75, times, now we go through each little part, 0.60 times F sub u times the net shear area, which was 4.406 inches squared. So don't write that in there. We're going to change it here in a second. And then we add to that UBS F sub u times ANT, which is the 2.511. So I'm going to correct it here. Sorry about that. So this needs to be the net shear area, which is 4.406 inches squared. And here we use the net tension area, 2.511 inches squared. All of this has to be limited by shear yielding along the shear surface, the shear failure surface. So that's 0.60 times the yield stress, which is 36 KSI, times the gross shear area, 6.064 inches squared, plus, and then we have the same factor, UBS times 58 KSI times ANT, which is 2.511 inches squared. I'm going to multiply all of this times 2, okay? Now I did this because I have 2 channel members, okay? So all my calculations for ANT, ANV, and AGV was just for one channel of the double channel member. So now I need to multiply by 2 because I have a channel on the front side of this connection. I have a channel on the back side of this plate that I can't see. So now we just have to work through the calculations. We'll see that the first 2 terms that correspond to fracture on the net shear area and fracture on the net tension area give us a higher capacity than we get for the shear yielding on the gross shear area plus the fracture on the net tension area. So we see that the second limit controls will take 276.62 kips, multiply by 0.75, and then again times 2 because we have 2 channels in the connection. That gives us that for block shear, P sub u would have to be less than or equal to 414.93 kips in this particular connection. All right, well, I hope you're rocking these block shear calculations and everything's going smoothly for you. I'm going to speed up the videos a little bit, and the next block we'll see in the net tension area, we're going to have to do something for a diagonal path, kind of like we did when we did fracture for this same example. All right, so as you can see, our solution will have to contain more free body diagrams for this connection. I've gone here on a diagonal path, and so now I want to just talk you through how do you calculate the net tension area for this diagonal path. Well, just like fracture, we're going to take the width, 7.5 inches, and then we're going to subtract out how many bolt holes it runs through. So the red path runs through a half a bolt diameter at the top, one bolt, and then a half a bolt diameter at the bottom. So that gives us a total of 3 effectively 3 bolt holes that the red path cuts through in the transverse direction. So that's why I'm going to have the -3 times the bolt diameter, 3/4 of an inch, plus 1/8 of an inch, again for the oversize of the hole, plus the potential damage for drilling that, punching that hole. Because I went on 2 diagonal paths, just like in fracture, I need to add the term s squared over 4g. All right, so I've gone ahead and I've added 2 of these terms because on my net tension area, I've traveled 2 diagonal paths. And you can see there, s squared over 4g is tucked away. S is the longitudinal spacing. So the longitudinal spacing on that red diagonal is 3 inches, and the transverse or the gauge spacing for both of those red diagonals is 2.5 inches. So that's why I've included that term. So if you have questions on the s squared over 4g term, I'd recommend you go back to the videos on calculating fracture and staggered bolted connections. But otherwise, I think if you understand that, you're ready to move forward. We calculated the net tension area as 2.530 inches squared. The net shear area and the gross shear area for this particular block are going to be the same as block number 1. And so there's no need to recalculate them here. Just go back to block number 1 and we'll see that ANV is 4.406 inches squared and AGV is 6.064 inches squared. Once we have this, we just have to run through our block shear capacity equation and we'll get an answer for block number 2. All right, so I'm trying to give you some tips and tricks to limit the amount of calculations you have to do. So as I've recognized, ANV and AGV were the same as block 1, and since ANT was larger than block 1, there was really no reason to make the calculations in this particular case. So block 1 will control relative to block number 2, and so therefore we can just move on to block number 3 to start checking it. Just like we did in fracture, we want to make sure that blocks that fall behind the front line of the bolts don't control the design. So that's what I'm going to take a look at in block number 3. So the next block I would check is the block here that I've sketched. So we don't really have to consider the blocks that rip out the sides because in this particular, for the channel member, ripping out the side would mean ripping out the entire top or bottom flange of the channel member. And so that's not typically likely. So I would focus on kind of these blocks in between the bolt holes, at least for this channel member connection. So go ahead, try these calculations out, check your answers against them, make sure it makes sense to you, and I'll catch up to you in a bit. Hope you're killing these calculations. Don't forget, whenever you consider blocks that are behind a few line of bolts, we have to use that multiplier to increase because it's not the same load as was considered in blocks 2 and 3. Finally, don't forget to check the gusset plates. So on my last page, I have some sketches. We're going to look at some of the gusset plate connections. Now, everything will kind of be the same, but for the gusset plate, we will want to consider the possibility that the gusset plate can rip out the side, but we will have less blocks to check because relative to the gusset plate, we don't have as many possibilities in terms of like the diagonal pass to consider. So go ahead and give the gusset plate calculations a try, and you can use the rest of this video to kind of make sure you're getting the same answers as I am. Once we completed all the blocks, we just need to go back and see which of the 6 blocks controlled for block shear. We found that to be block number 3. Block number 3 had a capacity of 354.47 kips. All right, almost to the end. The last thing to do is to check the fracture and the yield capacity that we had from the lesson 17. So we see that in the case of this double channel tension member, the block shear limit state would control. We still have to go on to check bolt limit states though, and we'll talk about that in a future lesson. Alright, well, as you can see, living the block shear life can be kind of exhausting sometimes, but very important to make sure all our connections are safe and all our members are designed properly.